Welcome back to the deep dive. Today, we're tackling something huge. We're looking at maybe the most famous equation ever, Sora, and really asking, okay, where does that actually come from?
Yeah, what's the physics behind it?
Exactly. We're diving into Chapter 16 of the Feynman Lectures, Volume I, Relativistic Energy and Momentum. And this isn't just, dry theory.
Not at all.
It's really the heart of modern physics, and it gets pretty weird pretty fast.
It does. And the goal for you, the listener, is to get a real solid conceptual grip on how figures like Einstein and Poincaré just fundamentally changed how we think about mass and momentum and energy.
Moving way beyond Newton.
Totally beyond Newton. We have to understand what happens when things get close to the speed of light. It forces a whole new way of thinking.
And Feynman starts us off, interestingly, not with math, but with an idea, almost a philosophy. The principle of relativity.
That's right. It all comes down to your frame of reference.
And there was real resistance at first, wasn't there? The idea that time could slow down.
Yeah.
It just sounded absurd.
Completely absurd. Until the experiments basically forced everyone to accept it.
So what's the core principle?
Well, it sounds simple enough. The laws of physics, all of them have to look the same, give the same results for any observers who are moving at a constant velocity relative to each other.
These are the inertial frames, right?
Exactly, inertial frames. So if you're sealed inside a spaceship, coasting smoothly, you can't do any experiment inside, drop a ball, measure a spring to tell you if you're moving or sitting still.
Everything behaves exactly the same.
Just like on Earth. Assuming Earth is a good enough inertial frame for the experiment, which it usually is.
And the really big philosophical jump here is rejecting absolute velocity. You just can't know how fast you are absolutely moving. Speed only makes sense relative to something else.
You need that external reference point. Look out the window. Compare yourself to another ship or a planet.
But then light comes along and messes everything up.
That's the kicker. The critical observation, the one that breaks classical physics, is the speed of light. About 186,000 miles per second.
And it's always the same.
Always the same. For everyone. No matter how fast you're moving towards the light source or away from it, you measure c. Always.
Which completely contradicts the old way of just adding velocities. If you run towards a thrown ball, you see it coming faster.
But not light, it's still c. And that single fact forces us to rethink everything about space and time. They can't be separate and absolute anymore.
So just to clarify, though, this principle only applies to uniform velocity, right? Straight line, constant speed.
Yes, exactly. Feynman points this out. If your spaceship starts rotating, well, you can feel that.
Centrifugal force.
Right. You don't need a window to know you're spinning, so rotation is detectable internally. It's different from uniform linear motion.
Okay, so this constant speed of light, this relativity principle, it leads directly to probably the most mind-bending consequence. Time dilation.
Yeah, things get weird with time.
And the classic way to picture this is a twin paradox. Tell us about Peter and Paul.
Okay, so you have twins. Peter stays on Earth. Paul gets in a super fast spaceship, zooms off, travels for a while at, let's say, a significant fraction of the speed of light, turns around, and comes back.
And Peter, watching Paul through a telescope, let's imagine.
Yeah.
What does he see happening to Paul?
According to relativity, Peter sees everything about Paul slowing down. Paul's clock on the ship ticks slower than Peter's clock on Earth. Paul's movements, his heartbeat, even his thoughts. From Peter's perspective, they're all happening in slow motion.
So when Paul finally gets back...
Peter expects Paul to be younger, to have genuinely aged less.
But wait, isn't motion relative? Why wouldn't Paul see Peter's clock running slow? Why isn't it symmetrical? Who is really younger?
That's the paradox, but it has a clear resolution. The situation is not symmetrical.
Because
Paul had to change his frame of reference. To come back, Paul had to decelerate, stop, turn around, and accelerate again.
the acceleration.
Exactly. Paul experienced forces, G-forces. He was pushed back in his seat, or forwards. He left his initial inertial frame and then returned to it. Peter, just staying on Earth, we approximate it as a single inertial frame, didn't go through that acceleration.
So it's the turning around, the acceleration, that breaks the symmetry and makes Paul definitively the younger twin upon return.
That's the physical difference. It's not just about the speed, it's about the change in velocity.
And this isn't just a thought experiment, right? This happens.
Oh, absolutely. It's proven constantly. The mu-mesons Feynman talks about are a perfect example.
These are particles created high up in the atmosphere.
Right. Cosmic rays hit the upper atmosphere, create these mu-mesons. Now, these particles have an incredibly short half-life, like microseconds.
So short they shouldn't even make it down to the ground before decaying.
Based on their rest lifetime, no way. They should vanish way up high.
But we detect them down here on the surface. Lots of them.
We do. And the reason is time dilation. Because they're created moving so incredibly fast, close to the speed of light, their internal clock slows down relative to us observers on Earth.
Their short lifespan gets stretched out from our perspective.
Exactly. Time literally runs slower for them, allowing them enough time in our frame to reach the ground before decaying. It's amazing.
Okay, so time is relative. What about velocities themselves? The old Dollity's u plus v Goral doesn't work anymore because you could theoretically exceed c.
Right, that simple addition is out. We need a new way to transform coordinates, space, and time between moving systems.
And this is where the Lorentz transformation comes in.
Yes, Hendrik Lorentz worked out these equations. Unlike the old Galilean transformations, which treated space and time as separate, the Lorentz transformations mix them up. Time in one frame depends on both time and position in the other frame, and vice versa.
It's a fundamental link between space and time.
It is, and from these transformations, you can derive the correct formula for adding velocities relativistically.
Which looks more complicated. There's that denominator.
Yeah, the relativistic velocity addition formula. If a ship moves at speed relative to us, and something inside moves at Fugger relative to the ship in the same direction, the combined speed phase we see isn't just O plus Vxa, it's 1 plus Vxa divided by $1 plus UVX2.
Okay, that denominator, $1 plus UVC2. What's its significance?
That denominator is everything. It ensures that the result, Vx, is always less than or equal to c. You can plug in speeds in a mu-mesons that are both very close to c, but because you're dividing by something greater than 1, the result never actually exceeds c.
It's like a built-in speed limit regulator in the math.
Pretty much. It mathematically enforces the cosmic speed limit.
Let's do the ultimate test, Feynman suggests. Spaceship moving at, say, 0.8 c relative to Earth.
Okay.
Astronaut inside shines a flashlight forward. The light beam moves at c relative to the astronaut in the ship.
Right. Vx is a c.
Classically, we expect to see the light moving at 0 del is 8 cent plus c equals 1.8 c as to Zell, faster than light.
But plug C dollars into the relativistic formula. You get $1 plus CC2, which simplifies to $1 plus CC divided by 1 plus CC.
Right.
If you do the algebra, that fraction simplifies exactly to C.
Wow. So even adding a velocity u to c using the correct formula just gives you back c?
Exactly. The speed of light is the absolute maximum. Relativity demands it. Adding C to anything else still results in C.
Okay, this is forcing major revisions. Time is relative, velocity addition is weird. What about mass? In classical physics, mass is just constant. pp equals mv dollar.
Right. Mass is just a fixed property of an object. But if we want to hold on to one of the most fundamental principles in physics, the conservation of momentum.
Which we definitely do.
Absolutely. If momentum must be conserved in all inertial frames, even with these weird time and velocity rules, then something else has to give, and that something is mass.
Mass can't be constant anymore.
It can't be. For momentum to be conserved correctly under a Lorentz transformation, the mass in the equation pmv bella must depend on the velocity dollar.
The faster something goes, its mass changes.
Yes.
Right.
Specifically, it increases.
How does Feynman show this? He uses another thought experiment, right? A collision.
A very clever one. Imagine two identical objects. They have a glancing, elastic collision. They bounce off each other. Now, analyze this collision from two different reference frames.
Okay.
One frame where the collision looks symmetrical, maybe the center of mass frame, and another frame that's moving horizontally relative to the first.
Right.
If you demand that momentum is conserved in both frames, particularly the momentum component perpendicular to the relative motion of the frames, the only way to make the math work out, given the Lorentz transformations,
is if the mass of the object that's moving faster in a given frame is larger than its mass when it's moving slower or at rest.
Exactly. The calculation forces you to conclude that mass must increase with velocity according to a specific formula.
And is it that same factor again?
It is. The relativistic mass dollars is equal to the rest mass dollar. That's the mass measured when the object is stationary, divided by the square root of $1 V2C2 tau.
$1 6T or 1 V2C2. It's everywhere.
That factor governs time dilation, length contraction, which we didn't really discuss but is related, and now relativistic mass.
And look what happens as Vela gets closest to towers.
Approaches dollars, UCC2 approaches 1, the denominator Sanic C2 approaches 0.
So the mass dollar goes towards infinity.
Infinity, which provides another way to see why you can't reach the speed of light. To accelerate an object with infinite mass would require infinite force or infinite energy.
So the changing mass reinforces the cosmic speed limit.
It locks it in.
Okay, relative time, weird velocities, changing mass. This brings us to the grand finale, energy, section 16 to 5.
The culmination, relativistic energy.
How does energy connect to this changing mass? Feynman relates it to work and kinetic energy, right?
Yes. He considers the work done on an object to increase its speed, which increases its kinetic energy, T, when you do the calculation using relativistic momentum and force.
You find that the change in kinetic energy isn't the classical $12 mil-v22 anymore.
No. You find that the kinetic energy gained, delta Tphis, is equal to the change in mass delta m times 2tu2, or T equals is mma2. The kinetic energy is the increase in mass compared to the rest mass, multiplied by 2 times.
Precisely. And this leads directly to the big one. If the increase in energy, kinetic, is the increase in mass times 2t22, maybe the total energy dollars is just the total mass times 2222.
P2 tas mz22. This equation implies that the total energy of a particle is its relativistic mass times 222.
And since 1/8 is middle b2 scare 1 v22.
You can expand that for low speeds, and you find any dollars is approximately Nessie2 plus 12 middle v222.
Ah, so the total energy is some intrinsic rest energy,
Yeah.
NSE22, plus the familiar kinetic energy, 12 middle v22 test at low speeds.
Exactly. The Nessie222 term is revolutionary. It says that even when an object is sitting perfectly still, it has an enormous amount of energy locked up in its rest mass, E dollars equals an mz22.
Mass is energy, energy is mass. They're two sides of the same coin.
They're fundamentally equivalent, convertible.
Let's make this concrete. Feynman uses an inelastic collision. Two identical lumps of clay, maybe, each with rest mass, inelastic dollars.
Okay.
They fly towards each other, collide, and stick together into one stationary lump. Kinetic energy seems to be lost, right? It turns into heat, sound, deformation.
Right. The collision is inelastic. Kinetic energy isn't conserved. It's transformed into internal energy within the final combined lump.
So what does NeMC2 say about the mass of this final lump? Let's call it Nia dollars.
Since the initial kinetic energy has been converted into internal energy, heat, etc., within the final object, and energy is equivalent to mass, that internal energy must contribute to the mass of the final object.
So the final mass now must be greater than the sum of the initial rest masses, 2 millidollars.
2 millidollars. The energy that was lost as kinetic energy hasn't vanished. It's now bound up inside the object, making it measurably heavier. Energy literally has weight.
That's incredible. Just by heating something up, you technically make it slightly heavier?
Technically, yes. Though the 2-to-2 factor is so huge that for everyday temperature changes, the mass difference is totally negligible. But it's real.
But where it's not negligible is nuclear physics.
Absolutely. This is the key. In nuclear reactions, like fission, where a heavy nucleus like uranium splits into smaller fragments,
the total mass of the fragments after the split is measurably less than the mass of the original uranium atom.
Right. There's a mass defect. That missing mass hasn't disappeared. It's been converted into a tremendous amount of energy. The kinetic energy of the fragments, radiation, according to what E equals delta mc22.
That's the source of nuclear power and nuclear weapons, the conversion of mass into energy.
It is. 1mc2 explains where that energy comes from. It was locked up in the mass to begin with.
Okay, before we wrap up, Feynman gives one final equation, a kind of master equation that ties energy and momentum together in an invariant way.
Yes, this is really important. It's E2222 equals m02c42.
Energy squared minus momentum squared times c squared equals rest mass squared times c to the fourth. Why is this so special?
Because the quantity 2c222 is an invariant. It has the same value in all inertial reference frames. Observers moving at different speeds will measure different values for the total energy dollar and the momentum of particle.
Right, because kinetic energy and momentum depend on velocity.
But when they calculate the combination 2c222, they will all get the exact same number. And that number is fixed by the particle's intrinsic, unchanging property, its rest mass, Hein dollars.
So dollars is the true fundamental identifier for a particle that all observers can agree on, regardless of their motion.
Exactly. It's the relativistic signature of the particle.
All right, let's try to summarize the huge conceptual journey we've taken through Feynman's chapter 16.
Okay.
We started with the principle of relativity, no absolute motion. Laws of physics are the same for uniform observers.
Which, combined with the constant speed of light, forced us to accept that time is relative, time dilation is real.
We saw the twin paradox resolved by acceleration and saw mu-mesons as proof.
Then we needed new rules for velocity addition, governed by Lorentz transformation, ensuring c is the ultimate speed limit.
To conserve momentum, we had to accept that mass increases with velocity, becoming infinite at c.
And finally, we unified mass and energy with E-SEM2 at 2, showing that mass is a form of energy, and energy has mass, which explains nuclear energy release.
And tied it all together with the invariant E22C2 equals M02C42.
It's a complete overhaul of classical thinking, really. Newton's laws are just approximations for low speeds.
So here's the final thought to leave you with. Building on this idea of rest energy, E dollar equals indice2. If a particle's fundamental identity, its rest mass, nem dollars, is really just a package of internal energy, what does that imply about the structure of fundamental particles? What is going on inside an electron or a proton that constitutes this rest mass energy? We've accounted for the total energy, but
what is that energy at rest? What internal dynamics, what configurations make up $6? We know it's there, we know it's invariant, but fully understanding its origin.
that's still a frontier, isn't it? What else is tied up in that rest mass that we haven't fully unpacked?
A deep question, still driving physics today.
Well, that was quite the dive into the deep end of relativity. Thank you for joining us.
Thanks for listening.
We'll see you next time on The Deep Dive.